All right, if you've been keeping tabs on climate tech, you already know that capturing carbon dioxide straight out of industrial exhaust is pretty much the critical challenge of our time. But actually doing it efficiently, safely, and affordably? Well, that's been the ultimate bottleneck. So in today's explainer, we are going to explore a technological architecture that completely flips the traditional script. We're moving away from harsh, volatile chemicals and diving into a system that is just incredibly elegant.
We really have to start by asking a massive question, one that the industry has literally been wrestling with for decades. How do we clean industrial emissions without creating toxic waste? See, for a long time, the default answer to capturing carbon has been using amine-based solvents. But amines have a pretty dark side. They degrade over time, they need massive amounts of energy to run, and worst of all, they can produce highly toxic, carcinogenic byproducts. If our end goal is to clean up the planet, we simply cannot rely on a process that just generates more hazardous waste at a massive scale. We need a solution that's as clean as the problem it's trying to solve.
To really get a feel for where this new tech fits in, let's look at the standard capture pipeline. Going from the industrial source on the left to storage on the right, our focus today is planted squarely in the middle, the capture facility. By fundamentally changing the chemistry and the mechanics inside those capture tanks, we drastically alter the economics and the environmental footprint of literally everything that follows down the line.
Here is our roadmap for today. First, we'll step inside the carbonate scrubber itself. Then, we'll break down the closed-loop chemistry, compare the economics of carbonates versus amine systems, and finally, look at the ultimate solid carbon end product. Let's get to it.
Section 1. Inside the Carbonate Scrubber. Let's see exactly how we turn a hot, dirty smokestack into a purified stream of gas.
Imagine you're a flue gas molecule traveling through this system, through the oxidation, cooling, absorption, and regeneration stages. This isn't just a single magic filter. It's a meticulously designed sequence. First, the incredibly hot and polluted gas leaves the industrial plant. But instead of immediately hitting the carbon capture chemicals, which would honestly just destroy them, the gas enters a pre-treatment oxidation phase. By injecting oxygen to create radicals, the system actively destroys harmful pollutants before they even reach the scrubber. It acts as a crucial protective shield for the entire setup.
Right, so after that gas is cooled down to a much more manageable 80 to 120 degrees Celsius, it flows upward into the scrubber tower. Inside, the gas meets this cascading shower of sodium carbonate slurry. Think of this liquid salt mixture as a highly specialized chemical sponge. When the CO2 makes contact, it chemically transforms into bicarbonate, effectively trapping the carbon inside our liquid sponge, while the clean air safely exits right out into the atmosphere. Now, once our liquid sponge is completely full of CO2, we have to wring it out, right? The liquid gets pumped into the regenerator vessel and heated. But here is the absolute genius part. It only needs to be heated back to about 80 to 120 degrees Celsius. That means we can simply use the free waste heat the plant is already generating. As the liquid warms up, it releases a stream of highly pure CO2 gas, and in doing so, the liquid chemically reverts right back into sodium carbonate, totally ready to be sent back to the scrubber to grab more CO2.
Moving on to Section 2, the closed-loop chemistry. How in the world do we keep this process running without constantly buying new materials? Just look at this retention rate, greater than 95 to 98%. That is the incredible retention rate of the sodium carbonate in a properly designed loop, meaning it behaves like a true closed-loop solvent. In older legacy systems, capturing carbon meant you had to constantly buy new chemicals because they would break down or wash out of the system. That was just a massive ongoing expense. But with this modern carbonate architecture, over 95 to 98% of the chemical is retained and recycled over and over again. You aren't burning through materials. You're simply utilizing a chemical vehicle that picks up CO2, drops it off, and goes right back for more.
So what's the secret sauce for keeping those chemical losses at basically zero? It actually happens upstream. If sulfur dioxide and nitrogen dioxide from the industrial exhaust are allowed into the scrubber, they permanently react with our liquid salt, turning it into unregenerable sulfates and nitrates. It basically kills the sorbent. But because our system pre-oxidizes and removes those exact threats early on, the carbonate liquid stays pure. You add in some high-efficiency mist eliminators so the liquid doesn't accidentally spray out of the chimney, and boom, you have a nearly perfect perpetual capture loop.
All right, Section 3, Carbonates versus amine systems. It is time for an economic showdown.
Let's talk money and look at the upfront capital expenditure, or CapEx, for a standard 50-megawatt plant.
Traditional amines require these complex towers of expensive, corrosion-resistant stainless steel, plus massive modifications to the plant's boiler just to provide high-pressure steam. You're looking at coming in anywhere from $40 to $65 million. Carbonates? Just $14 to $25 million. They utilize simple steel tanks and operate on basic waste heat. The barrier to entry for clean tech literally just got significantly lower.
And the savings continue day to day. Carbonate systems are obliterating amines when it comes to operating expenses, running 2 to 4 times cheaper per ton of CO2 captured. And that's simply because they rely on free waste heat and affordable soda ash. Amine systems cost between $38 and $65 for every single ton of carbon they capture, largely because they steal high-value steam from the power plant to regenerate the solvent. Our carbonate system, it costs a mere $12 to $23 per ton.
But hey, beyond just the financials, we absolutely have to talk about safety. While amines produce highly toxic, carcinogenic waste that requires super expensive handling, our carbonate system leaves behind only benign, safe salts. I mean, this cannot be overstated. If we're scaling carbon capture to a global gigaton level, we cannot create a new ecological disaster in the process. The waste products from an amine plant are hazardous and strictly regulated. The trace waste from a carbonate loop, it's literally just non-hazardous salts like sulfates and nitrates. It is radically greener, immensely safer for the facility workers, and infinitely better for the surrounding communities. Finally, Section 4, the ultimate solid carbon. Let's see how this all integrates with the CO2 Crusher technology. To push those operating costs down even further, facilities can actually manufacture their own carbonate sorbent right on site. Using a chloralkali cell, raw salt water is converted into sodium hydroxide. Combine that with a little bit of the captured CO2, and just like that, you've synthesized your own sodium carbonate sorbent right there at the plant. Then, the pure, clean CO2 gas that gets released from the regenerator doesn't just get pumped underground. It gets fed directly into a specialized conversion reactor, known as a crusher, which permanently transforms the gas into solid carbon.
It really all comes together in this one beautifully elegant equation. We are taking the world's most abundant resource, salt water, and the world's most problematic waste product, industrial carbon dioxide, to create a completely self-sustaining industrial ecosystem. We mix them together to create the very sponge that cleans the air, and the final output is a highly valuable, perfectly stable, solid carbon material.
So we've basically just seen the blueprint for a clean industrial future, vastly superior chemistry, the complete elimination of toxic waste, and all at a fraction of the cost. The technology is proven and it's ready to go. The only question left is, how quickly will global industries abandon their toxic legacy systems and actually flip the switch?